संतोष जी, वो उधर लाइन लगी है, देखो ना। 13 पे डालो, सब 13 पे। ठीक है, चलो। ओके। So, hello everyone. We will start the session in next 5 minutes, or maybe 2 3 minutes. We will wait for other learners to join so that they can interact and clear their doubts. Thank you. So let us start the session of the day. So hello, hi, namaskar. I am Prashil. I am a Prime Minister's Research Fellow at IIT Mumbai, and here we are studying advanced thermodynamics and molecular simulations. As I am telling you multiple times that we are learning advanced thermodynamics, right? And then second part of this course is application of these thermodynamic principles that we have studied to solve or find out properties of a model system. That means we are doing molecular simulations. Molecular simulations, right? This we have studied in the first half, and this we are studying in the second half. Here, these principles you already have studied in your undergraduates, and we are giving some statistical mechanical background, right, to those already learned concept, and those application the application of those we are finding it in molecular simulations, right? So what we are essentially doing here is we have a system, macroscopic system. So we have a macroscopic system, and we are taking a very small part of it to get a small system, which is a bigger system, which is a part of a bigger system. Again, to give you a real life example, consider ice. This is ice, all of you have seen, and it is kept on a surface. So this is a piece of ice that is kept on a surface. What we are essentially doing is we will take a very small part like this. What do you see? You will find one surface, right? Some surface is there, and there is some ice molecule. That means there will be water, right? Ice is essentially water. Some sort of structure will be there, right? So this is a combination of H2 n times of H2. So this is a macroscopic system. What are the dimensions of this system? You would find that it's in centimeter or meter. And if I want to study how it melts and after certain time when it comes in equilibrium, when it is kept at a room temperature, upon keeping what are its equilibrium properties? What are its equilibrium properties if I want to study these things? Then how much time it takes for the melting and understanding the properties? You know that it will take minutes and hours. That's where the idea comes that the system that we are now studying is having the dimensions of this centimeters and minutes. When we take a very small part of it, you will find that the system is in angstrom scale, because you know what is HOF bond length, it's approximately 1 angstrom or 2 angstrom, right? So we are going into angstrom scale, and I will tell that okay, the fluctuation of this bond length, that it vibrates around a mean position, and this vibration, what is the time period of this vibration around this mean position is in femtoseconds. It is in femtoseconds. So now you can imagine we have gone from centimeter scale to angstrom scale. Similarly, in the time, because when we go that much of deeper, the events that happen, the events that happens at that scale are in femtoseconds or nanoseconds or picoseconds. So I'll write femtoseconds or picoseconds, which is 10 to the power minus 15 seconds, and picosecond means 10 to the power minus 12 minus of 12 seconds, right? So this is the molecular length and time scales we are targeting, right? And for that only we studied the statistical mechanics, right? Statistical mechanics. So essentially my system will look like a box which has a surface, right, over which there is water in a crystalline state. This portion is also filled, right? Everywhere it is there. Over a surface, right, there is water or ice which is present over the surface. And for example, if this molecule is present here, there is another molecule is present over here, and the distance between these two is more than, for example, 10 nanometer. The interaction between those two molecules will be very very the interaction will be negligible interaction between particles or atoms separated at larger distance, right? So if the distance between them is very large, then it is, the potential, right? This is how our interaction potential is, and you will find this is 12 angstrom, which is equals to 1.2 nanometer. So I'm telling that okay, when I am having an Lj interaction energy potential, or if you just combine total interaction energy is equals to bonded interaction energies plus non-bonded interaction energies that we have studied, right? Even if you do that, you will find out the curve will look like this, some function like this, right? So what you will find after 20 angstrom, which is equals to 2 nanometer, max to max I will go up to 30 angstrom, which is 3 nanometer. You will find the interaction energy is negligible. Those two atoms and the molecules, whatever, one is over here, other is over here, these two will not interact. There is no relation. If you want to imagine these things, okay, consider a person. This is moon and earth, right? There is a person which is standing over here on moon, another person which is standing, right? What and all movements this person is making are independent of the movement that person is making over here. Even if you don't go that far distance, just consider two person, one is in Delhi, other is in Mumbai. The rest, right, the rest system is other molecules. You will find the movement that is happening over here, it is independent of the movement that is happening. So beyond certain distance, the interaction energy decreases, right? And it is zero, it is zero beyond certain distance. That's what, even if I consider this system, and what is happening, you see that we have a ice which is kept on a surface, and there is surrounding air, nitrogen could be there, or you can create a vacuum. That is nothing is there. Not vacuum in the sense there is nothing, right? So instead of this 10 nanometer or some higher distance, we will not take that much of larger distance, because number of molecules will be higher, the distance is higher, right? Number of molecules are higher, because of which the computational time that is required to get the equilibrated state will also be higher. That's why what we do, instead of considering this, we just cut off it at some distance. We will not take this much big system, take a small system, and you will find what happens. Let's say you will find the interaction energies are dominant up to certain layers over here. Beyond crossing certain distance, it's work like behavior. That means the whatever movements this fluid is making over, it has no influence over this interactions that are occurring at the interface, right? So if I consider the system and plot it like this, horizontal, this is my surface. Some molecules are adsorbed over here. Then the system is having a random arrangement, you will find. And when you calculate density of the molecules, you will see more and more molecules are placed over here, and beyond certain distance it is almost constant. So even if you take this much long system or not, or if you take this much long distance, right, to define the system's dimension, for example, this length of the box is 200 angstrom or 100 angstrom, that doesn't matter. So beyond this there is no interaction energy. And then what comes is this region is entirely the same, correct? So what we can do, and after that you can see there is some air, so you can directly skip this portion in between, and then you may have the system like this, that you are having a surface over here, ice is kept, right? That means water molecules in the crystalline structure, right? Over here, water molecule in the crystalline structure, and then there is vacuum. There is vacuum over here. This is my surface, water in crystalline form, water in crystalline form, and then there is vacuum over here. Similar sort of system simulate. You can simulate. So this is how my system will look like at microscopic, or I would say this is a representation of a molecular system. We are considering fundamental particle as atom, and we are seeing how it is behaving over the time, correct? So now we have decided how the system would look like, right? Now the part is how to inform. The question is how to tell computer that your system, how to inform, how to tell that this is your system, how to tell the computer about your system, how to tell, that is the question. So again, to give you an example, if this surface is sandstone rock, it is a rock and it's made up of sandstone. Sandstone means SiO2. So there are silicon atoms and oxygen atoms, uh, right? So we have silicon atoms and oxygen atoms. So they will be having some crystal structure, for example simple cubic structure where we have atoms on the lattice position. We have atoms on a lattice position. So this is how my lattice would look like, correct? So one of the atom could be silicon, oxygen, here it is oxygen, then here it is oxygen, here it is silicon, and then again it is oxygen over here, then again silicon is here, right? So this is SiO, some structure is there. And you know from the XRD, that is X-ray diffraction, it is well known. Okay, what are the lattice parameters? A, B, C. So you have an understanding of, okay, what is the lattice parameter. You also know what is the lattice angle. So A, B, C, alpha, beta and gamma, these are my lattice constants or lattice parameters. So if I know the coordinates of this particular atom as 0 comma 0 comma 0, then what is the lattice constant? We know alpha, beta, gamma, and what are the parameters. So for example, if A is equals to 3, then what is the next atom? The coordinates of this atom would be 3 comma 0 comma 0. Similarly, based on the angles alpha, beta, gamma and the lattice parameters, that is A, B, C, we can get the coordinates of a crystal. And then we repeat this unit cell. This is my unit cell. We repeat that unit cell n times. We repeat this unit cell n times to get a surface. So the surface can be obtained. So the surface can be obtained by by repeating the unit cell. Right? You replicate this unit cell, you are going to get a surface. It is not necessarily that you have to repeat in only one direction. You can repeat in y and z direction, right? And then you can have a complete structure like this. So here you can see you have created one from here to here, one surface you have created, right? Now over this surface, so this is the surface which you have created or which we have created, right? The unit cell, we know the crystal, we know the lattice parameters, and using these lattice parameters and the dimensions or the coordinates of the unit cell, we have created one surface. The next step is to create water, right? If it is ice, again you have to get the coordinates of ice XRD structure, and then you can melt it, right? Or if you just want to study water, then in that case you have to randomly generate the coordinates of water. So you know I have a water. How does it looks? H2O. HOH, correct? So this is my hydrogen, this is my oxygen. I know from the literature what is the angle. It is close to 108. right? 108. I know the coordinates of one of the atoms 0 comma 0 comma 0, right? I will have to insert it in the box, and let's say box is having a length. This is my box which has a length Lx, Ly, Lz, right? So I'll generate the coordinates of this atom in this box, and upon generating one atom I'll ensure, okay, what is the bond length distance at that location. Only I need to generate the coordinates of hydrogen. Again, based on the bond angle, I know what should be the coordinates of another hydrogen atom. Similarly, I'll generate the positions randomly. I will generate the positions of these atoms randomly, right? The only take care that I need to take is these atoms should not overlap. Correct? These atoms should not overlap. Right? So we know overall altogether we have generated the coordinates of the surface. We have also generated the coordinates of the water. We can generate them on lattice if we want to study ice. And we can generate the coordinates randomly if we want to generate the position of water, because it is a liquid, so it is not a crystalline structure, and if it is not a crystalline structure we can randomly generate the coordinates where the molecules are continuously moving at particular temperature T, right? If the temperature is higher, movement will be higher, and temperature is higher, movement will be higher, because they are having higher velocities. The molecules will have higher velocities. And if the temperature is less, they are having lesser velocity. So what we did, we have generated the coordinates. So now my system is ready. This is my surface for which I have generated the coordinates. Right? And then here it is. Coordinates also generated for water randomly, ensuring we have to ensuring that no two atoms can overlap. No two atoms overlaps. Right? Because we know this is how our potential will look like. You can see if one atom is sitting over here, other atom is sitting over here, the interaction energy is close to zero. It is close to zero. But if another atom is sitting over here, you can see what is its interaction energy. This is my interaction energy U as a function of R, and here it is R. So Y is my energy and X is the distance. Similarly, if an atom comes and sits at this distance, this is my interaction energy. Some minus epsilon value, some fraction of epsilon value, or multiplication factor of epsilon value. And hence, if the molecule crosses this distance and goes over here, you can see the energy is infinite. That means if we do not ensure that atoms are not overlapping, right, what will happen? Atoms will overlap, and because of overlap of those atoms, energy is equals to infinity. Energy U is equals to infinite. And since the energy is infinite, force as a function of r is also del u by del r, which is also equal to infinity. Correct? If the force is infinity, we know how to get the coordinates of the new atom, right? That we will discuss. That coordinates will also be very high value, and it is something that is something which cannot be simulated, because infinity is something that we can't be simulated. This cannot be simulated in computer. This cannot be simulated in computer. Correct? So we have to ensure that. So now, since we have generated the coordinates, we took care of that the coordinates are not overlapping. That means our system is having some energy. But still, you can see from this curve, if two atoms are not overlapping but they are very close, if they are very close, then the energy is also very high. Not infinity but very high value, therefore force will also be very high value. And if the force is very high, that means again the system is unstable. That's where we have to ensure these things, right? Now what we did, we have generated the coordinates, we have ensured that okay, overlapping is not there, and atoms are far away from the each other, right? But then what should be the distance? If even though we ensure that our atoms are not overlapping, still some of the atoms will be having a distance which is less. So if there is less distance between these two particles, right, these two particles are close, then the energy is very high. How to get rid of this? For that we do something called as energy minimization. What is essentially done in this process is, let's say I have the coordinates, right, and you know that okay, one of the atom is, these two atoms are closer. Since they are closer, their energy value is very high. We want to decrease the we want to decrease the energy. Since we want to decrease the energy, we want these atoms to be at a distance where the energy is minimum, right? So we want energy to be lesser value, therefore we will randomly, let's say this atom is A, this atom is B, this atom is C. We will randomly displace atom A or B, anything. I am considering A for the timing, A, such that energy of the system is lower. Energy should be lower. Our objective is to decrease the energy. Now remember, if I am changing the location of B and I am keeping it close to the C, again energy will be high. So we have to shift that A such that the energy should be minimum. Energy should be minimum. So we have to find out that distance, right? So that is being taken care by the algorithm called as steepest descent algorithm. Steepest descent algorithm. steepest descent algorithm, right? Then once we are done with this process, whatever energy minimization we do is in step 1, this is my step 1, is not actual dynamics, right? That's where we are randomly displacing, right? This is not actual displacement, right? But we want the system to behave like, and it shows some dynamics, right? So that we can evaluate some of the properties. Therefore we do something called as equilibration. Equilibration, what we essentially are doing in this process is we are decreasing the energy of the system. Again, energy decrease. How? There are two approach. One is molecular dynamics, other is Monte Carlo simulations. Here random displacement happens, right? And over the large number of steps we do the simulation, we reach equilibrium. That means the energy of the system is not changing. Energy of the system is not changing. Correct? Similarly, we do MD simulation where we calculate, you know what is the U of R. You take the derivative dUR by dr, and then you get something called as force. And how it will be used, you know, from the Taylor series, simplest algorithm is Taylor series over here. X at t plus delta t is equals to x at t plus delta t into dx by dt plus delta t square divided by 2 factorial into d2x by dt2. You know this term as velocity, and this is my acceleration. A acceleration is equal to force upon mass, and force you already have from here. Velocities, you know, and that's where we are going next step. And we are doing multiple iterations we do, so that ultimately you will find that systems energy decreases, and as per the first law, entropy increases. Entropy increases, which is what we want. That means we are going to an equilibrated state, right? And once we reach that equilibrated state, we sample the data points, we see how molecule is moving at equilibrium, and then in the step 3 we see that molecule moves and energy fluctuates around mean position. That means earlier energy was like this, later on it is fluctuating. Fluctuates around a constant value, so instead I'll write constant. Energy is constant. We say that okay, now the system has reached the equilibrium, and then for each and every step that we perform afterwards, we note down the coordinates of all atom. That is called as production run. Production run, where we note down the coordinates of each and every atom in each step. So stepwise data collection, stepwise coordinates and velocity collection, velocity of each particle. We do. And using this velocity we get kinetic energy, using the position we get potential energy, and various other properties can be calculated using this simple approach. So this is how MD and MC works, molecular dynamics and Monte Carlo simulation works, right? Now based on this we will be solving some of the question. Please let me know if you have any doubts in the portion that we have covered, right? So that It will be helpful for us to solve the questions, right? So question number one is there already on your screen. You can look after it and then tell me what is the answer to question number one. We will be discussing this now. So I'll just quickly go through. So we are saying that okay, that we have a microscopic system, macroscopic system. We are taking a very small part of it, which has a atoms and molecules representations. Each of the atom will have some coordinates. It may be a crystalline structure or an amorphous or a liquid state or gaseous state, and accordingly we have to generate the coordinates. If it is a lattice, you have to take a unit cell, get the coordinates, get the lattice parameters, and then keep the coordinates of the unit cell. After that, upon repeating the unit cell, you will get the coordinates of the surface. You can create a surface. Then we want water, right? For that, we will be generating the coordinates randomly and ensuring that okay, there is no atom overlap. If there is overlap, okay, energy is very high, which is making the system unstable. So we want system to have atoms which are far apart where the energy is minimum, right? And upon creating that, we are generating the random velocities and then calculating velocities and the positions in next step using Worley algorithm, right? Where we have taken help of force and the velocities acceleration, right? And we are getting the energy lesser and lesser in each and every step. Upon certain number of steps, you will find that okay, energy is decreasing and it is a constant value now. It is fluctuating around a constant value, which is a constant energy we say. Once it is fluctuating around that constant energy value, we we note down, or we stepwise in stepwise manner we note down the coordinates. We store those coordinates and velocities to get and calculate the properties. That's all, right? So now based on this, we'll be solving some questions. It is there on your screen. Please try to solve. So question number one is, a typical time step in an atomistic molecular dynamics simulation is. This you know very clearly, right? Please tell me. Right. So here we have question which asks you okay, what should be the typical time step in an atomistic molecular simulations, right? So you can see over here in the first part of class this class we have seen, right? Okay, what should be the time step, right? When we go deeper and deeper at molecular length scale, you can see the events that happens, for example bond length fluctuation and all molecule movement that happens at the picoscales, right? Picosecond time scale. So if we want to, generally those are in picoseconds, okay, those are in picosecond, and that's where if we want to capture we have to take very small time step, right? If some event is happening in this picosecond time scale, right, then we have to have the time step in femtosecond so that every femtosecond we see and we can capture. Otherwise, if I am having an event that is happening in femtosecond, right, and if I take picosecond time step, so we are skipping some steps in between, right? We are not able to track this. So that's why the time step should be very small and according to the what? According to the need, right? Whether you want to capture what and all phenomena that you want to capture, it should be captured within that limit. It should be slow, and generally the time step is in 10 raised to power minus 15 seconds, which is femtosecond. 115 femtosecond, which is general. We can take 2 femtoseconds, 5 femtoseconds, that is also possible. Again, one more thing. For example, I am doing this simulations, and I know in this equation that we have already written, right, to get a next position we have to have the current position, and the velocity has to be multiplied with the time, right? So if I multiply with delta t, delta is a time step, that's what we are trying to look after. Okay, what is should be its value? If the time step is very high, then the next position will be very high, and we see quick displacement. If the displacement is high, there are chances, if your system is having very high energy, velocity is high, and if delta t is also very high, the displacement will be very high and particle will move and go out of the box. So there is certain explosion that may happen. That's why we need to take care of this, right? And that's where we have to have a very less time step, right? So the answer to question number one is this. Then question number two, which of this is not a thermostat used in molecular dynamics? So we are talking about molecular dynamics simulations where we have multiple ensembles, and in those ensembles we have to maintain the temperature and pressure depending on the ensemble time. Maintain temperature is constant, right? Majority of the ensembles will have temperature we have to keep constant, and pressure, for example in case of NPT, sometimes correct. So temperature has to keep constant, and to keep the temperature constant, how what we do, if I have milk, what is this? This is milk. I have to heat and maintain its temperature at 25 degrees Celsius, for example, or 35 degrees Celsius. If I directly heat, what will happen? If I directly heat, the temperature will keep on increasing, right? So nowadays there are sensors. If the temperature reaches that value, the burning stops, right? Or we can have a bath. We will be heating this bath, heating using bath, right? So this is hot water whose temperature I am maintaining, and then through this water's temperature, which is in the bath, I will maintain the temperature of the system, temperature of milk. So what is this? This is a type of a thermostat. We are using a bath, so this bath is a thermostat which is used to keep the temperature. Similarly, AC is also thermostat. What does it do? It removes the heat, right? Removes the heat upon work. We have to do the work by which it removes the heat from the system, from the room, right? That sort of things are called as thermostats, which maintains the temperature. What we do in case of Velocity rescale. So there are multiple types of thermostats. Velocity rescale is a thermostat. Langevin and Anderson. All of them are the thermostat. Whereas this is an algorithm, integration algorithm. So that's where I will tell. Okay, option A, C, and D are correct, which are the thermostat. Now we'll see just the function of these thermostats. We know that velocity rescale. How does it work? You know, half kbt is equals to half mv square. So you can see temperature is proportional to velocity. So T1 upon T2 is equals to V1 square upon V2 square. Right? Upon doing some number of steps, the velocity of the particle changes, because of which the temperature will change, and we want temperature to be at a constant value. So T2, that is next temperature, is equals to what is the current temperature. This is my set point, which is equals to current temperature into V2 square divided by V1 square. Correct? T2 is equals to this value. So this, or similarly, if you want V2 square upon V1 square is equals to T2 divided by T1 into V1 square. So V2 is the velocity that we have to adjust. This is a set velocity corresponding to T2. And what we have to do, you have to scale this velocity. So it is called as rescaling the velocities to get the accurate velocities which corresponds to the temperature that we want to set up, that we want to keep constant, right? This is V rescale. Let's say I have a system and I'm keeping it in a bath. So there is some fictitious particle, right, which is being used to decrease the temperature of the system, like this bath example that we have taken. We have to solve the equation of motion for the bath also. That is called as Langevin thermostat. And what Anderson thermostat does, we are taking some of the particles from the system, and then we are changing their velocities. If we change the velocity of some of the particle, the entire velocity of the system also changes. So this is what is the function of Anderson thermostats. So that's where question number 3 is also already solved. In Anderson thermostat, we randomly select the particles and change their velocities to match the Maxwell Boltzmann distribution at some interval, right? We are not doing this changing, alteration, everything in each step, right? We do this adjustment over 100 steps or 1000 steps that we have to give as an input. So we adjust slowly, right? And that is what is the Anderson thermostat. Option number C is there. So in question they have just asked only one thermostat. We have discussed all three thermostat, right? All three thermostat that we have studied. So in case in exam, if some questions comes, you will be able to solve, right? Now thermostats is required in which ensemble? You know, thermostat is required, we studied, it is required to maintain the temperature constant. So what and all ensembles are there? Canonical ensembles NVE. Canonical, microcanonical is NVE. Canonical is NVT. Isothermal ensemble is NPT, for example. Isothermal isobaric it should be. NPT, and this is my mu VT. So here you can see in all the all the ensembles we have to keep the temperature constant except in microcanonical. So option these three are correct. Thermostat is required to keep the temperature constant in these ensembles, right? Then the next question, Monte Carlo simulations. It is on the Monte Carlo simulation. So Monte Carlo simulations are difficult to parallelize, because we know that, okay, in Monte Carlo simulation we have to calculate the global energy at every step, unlike in case of MD simulations where we calculate what is the position of the atom using the U and velocity of each atom, right? So forces of each atom is different, velocities of each atom is different. So if you want to compute forces on each atom on and velocities and corresponding positions, we can do parallelization. But here we need a global energy based on which we calculate, okay, what is the whether that move which has been performed is acceptable or not. So global energy has to be calculated, right, together. Here it is individual calculation, that's why we can go for parallelization, but which is not the case in case of Monte Carlo simulation, which is option number C. Then autocorrelation function we have studied in last class also, right? What we are doing is any property is changing in each step, right? So what we do, we calculate average property taking delta t is equals to one step. In every step how it is varying, so m of t how it is varying. So tau is the step, n step, n equal to 1. Right now we are taking every one step, so n step is 1. So we'll calculate average property here, here, some value a b c d e. So we'll take average of this. For example, f is the average, corresponding tau is equal to 1. Then we will take two intervals, this 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 step up to, right, and then we'll calculate, okay, for example, f is done g h I j, correct. Average of them is k, for example, for tau is equals to 2. So we'll plot it for each and every step. Tau value 1, 2, and so on, and we'll calculate this, right. And then m at t and m at t plus delta t, that we will calculate, right. And this is called as autocorrelation function, that is c of tau. C is a function of tau. So we'll calculate any property at time t and time t plus delta t. For example, this and this, what is the relation? So the option is this. So we first calculate the value, multiply those things, this and this, whatever, first this or this, and then we multiply those values. What is the property at t and properties at time t plus tau, and then we get the value, average value. That's where we get the c of t, that is autocorrelation of a property. Pressure is typically computed in ideal gas equation, is in molecular dynamics simulations using van der Waals. No, it is very real, right? We know pressure is equal to pv is equals to nrt plus some correction terms. So those correction terms we calculate using varial, right? So this is the answer. Radial distribution of ideal gas. What is radial distribution function? It is called as g of r, which is equals to density at r divided by density of bulk or ideal gas. So I have a system which has some particles over here. What I'll do, I'll take a sphere and I'll calculate what and all molecules are there in that volume, right? So number of molecules per unit volume, number of molecules per unit volume we calculate, n by v. And similarly at larger distance also we calculate n infinity divided by v infinity, which is equals to density at infinity, which is the bulk density or which is the ideal gas density. So if it is an ideal gas, then obviously the ratio is g of r. If ideal gas and local density both are same, if it is an ideal gas, okay, this and these values are same, and that's where we see the g of r value is equals to 1 throughout r. It is not changing. Everywhere there is an equal probability to get the particle. So g of r will look like this as a function of r. So it is 1 irrespective of the distance, correct, irrespective of the distance. Then radius of gyration is, I have a system and I have a polymer over here. I want to calculate what is its diameter overall, I should say. Okay, what is it diameter? That is measured as rg, radius of gyration. So how do we calculate? We take a particular center of mass, that is rcm. We subtract each coordinates from that rcm, right, square, because the distance can be negative and it may cancel out, so we have to take square and summation. This is how we calculate for all molecules, summation over all 1 by n. So option is this, which is equals to Rg square. So option A is correct. Or there is another way. We will take each atom as a reference. So Ri minus Rj, each atom as a reference, summation over 2, right? Summation I is equals to 1, j is equals to 1 to n. So first we take r as a constant, we calculate its the position of other atom from that location. Similarly, we keep each particle as a reference. So we'll get what is the location, what is the average location of a second atom from the first atom, right? So that we get. So average distance we get. So here option C is also correct. Ri Rj to get the diameter of that polymer or ring particle, right? Then last question of the day, which of the this is most difficult to get using molecular dynamics? Ionic complexation, if one of the ion how it is interact with another ion. Formation of hydrogen bond also. Physical aggregation, if some of the atoms are aggregating. For example, uh, milk has some proteins are aggregating to get some coarser structure, right? So the sort of aggregation, everything we can get in MD simulation except for the crystal nucleation, because the time scale over which this crystal nucleation happens, it is in microseconds, right? And what is the time step? In the question number 1 we know that time step is 1 femtosecond, which equal to 10 raised to power minus 15 second, and this many seconds we have to hundreds of microsecond we have to simulate. 100 microsecond is equal to 100 and 10 raised to power minus 6 seconds divided by 10 raised to power minus 15 seconds. See, 100 into 10 raised to power minus 9 plus 9. These many steps we have to perform. See, these many steps we have to perform, then only we can get. And get, and running the simulation for these many steps is something which is difficult. But yes, with the latest advancement in the computational HPC high performance computing, we can now also see, okay, crystallization, people are now able to simulate these things. But yes, the phenomena that happens over time scale of seconds, microseconds, right, it is difficult to capture. So option D is correct. Option D is correct. Crystal nucleation, it is difficult in molecular dynamics. So that's all for the today's session. We have solved the questions. I hope that you guys have got good understanding of, okay, how to simulate the system, how to generate the system on lattice on computer, then get the position and coordinates in the next time in future, so that you can see the properties of the system, or you can study the properties of system in equilibrium. Correct. So this is about the today's session. If you have any doubts, please reach out to me, right? And we will be solving the questions in again coming class. Thank you so much for connecting. Have a good day.